Okay, we're going to piece together the other two lessons as to why we were doing properties of sums and drawing all these rectangles in this one right here. Okay, and we're going to find the area under a curve using the definite integral and right Riemann sums. So if you go back to that first video of Riemann sums that I made, this was the definition for a Riemann sum, that if you create an infinite amount of rectangles, you would get, and you sum them all together, this would be your width of the rectangle, delta x. And this would be the height of the rectangle, width times height being area for a rectangle. And you sum all those, that infinite amount, take the limit of it, you will get the good approximation of the area under a curve. This is also known as the definite integral. This right here is the definite integral. Okay, same thing. So I'm going to do two examples today from your homework for tonight. But write these steps down. Step number 1, you want to find delta x being from whatever interval you're given, b minus a divided by n being the number of rectangles. Again, we're going to leave it as n because we want an infinite amount of rectangles. Then you're going to find your x sub k. And the way that you do that, this is a right Riemann sum, by the way. There's a way to do it with left Riemann sums, but right is pretty simple. But you take a and you add that to delta x times k. Then you find your f of xk, which is actually the height of that rectangle. You plug it into this formula up here. We do our summation properties that we've been working on now for a couple days. And I will show you how to double check it in the calculator. Okay? So the first question we're going to do is actually example number 11 on the worksheet tonight. Let me get there. Okay. And the directions are the same. It's going to say find the area under a curve given this formula f of x, use limits of summation and definite integral. And again, what we're doing is think about it as we're going from 0 to 5 of 2x, so up 2 over 1, up 2 over 1. And we're going to draw an infinite amount of rectangles. Right rectangles, I guess it should start here. Bunch of rectangles. Okay? We're going to find the area under that. Okay? Well, again, the formula says that we take the limit of these rectangle areas. So first, step number 1, you're going to find delta x. And delta x is b minus a over n, where a and b are the intervals. So this a is 0, b is 5. So that's pretty easy. 5 minus 0 over n, or 5 over n. Then we find x sub k. And x sub k is also a formula. It's a plus delta x, what we just found, times k. Okay? So a is 0. I'm just going to put 0 plus 5 over n times k. Or actually, I'm probably going to write that as 5k over n. That's x sub k. Now, what's step number 3? What's f of x sub k? What do you think that would be? Well, that would be your x sub k plugged into your f of x function. So wherever you see an x, you're going to put x sub k. Whatever you got for x sub k, you're going to plug that right there. So you would get 2 times 5k over n, which is 10k over n. So now that we've got all that, we're now going to go back up to this definition, and we're going to write this one out with our f of xk function times delta x. So let's write this out. This would be the limit as n goes to infinity from k equals 1 to n of your f of xk times delta x. So that would be f of xk being 10k over n times delta x, which was 5 over n. So let's see if we can clean this up. This would be 50k over n squared. Now, let's use our sum properties. Remember my sticky note? I'm trying to get this to either be just a constant, just a k squared, or just a k cubed. And then the others I can factor out because it's just a number. I mean, if I wanted 5 rectangles, that would be a 5. So I'm going to factor that out. So let's rewrite this. Let me move this up here. I'm running out of room. So this would be the limit as n goes to infinity. And I'm going to factor out the 50 and the n squared. I keep saying factor out. I'm going to take that scalar out. And then I just have the k left underneath then. And that's good. So going back to my little sticky note here, I'm going to rewrite what the k summation property is equal to. N squared over 2 plus n over 2. So this right here is n squared over 2 plus n over 2 times the 50 over n squared. And then let's distribute that. So let's see, n squared and n squared cancel. 50 divided by 2 is 25. Plus this would be 25 over n. And if I take the limit of each one of those, the limit of 25 as n goes to infinity is just 25. The limit as n goes to infinity of 25 over n, though, we know that one goes to 0. So 25 is our answer. Let's just check it on the calculator. Remember this right here, this limit definition? It's equivalent to the definite integral from a to b of f of x dx. So let's rewrite this as a definite integral, which would be from a to b, a being your lower number 0, b being your upper number 5, of f of x. What is f of x? F of x is 2x dx. Now I want you to go to your amazing calculator and I want you to hit math and go down to where it says number 9, fn int. What? You're going to put 0. Above that, you're going to put 5. Inside the parentheses, you're going to put your definite integral function, f of x, which is 2x. And then it's going to leave you with d alpha something. Well, we're doing this with respect to x. 25, everybody. You know you did it right. All right? Pretty simple. Obviously, that's a simple one. Let's do a harder one. So this is number 16. I've actually left myself a lot of space for this one. We can do it, though. This is fun. All right. So this, I guess I like to write it as the, let's see, number 1. Let's find what delta x is. This is your a, this is your b. So it's b minus a over n. B minus a over n. So that's 1 over n. X sub k is a plus delta x times k. So A would be 1. Delta x is 1 over n times k, so that's just k over n. And then step number 3, f of xk. And that would be, now you're going to take this, you're going to plug it in for everywhere you see an x into that function. Ooh, that's a tough one. 1 plus k over n cubed plus 3. Yes, you have to cube it. But you're going to trust me because of the sake of time. And I have already factored it for you. Let me turn off this light. It feels like there's a glare. That's a little better. All right, so now we have this. Let's write out this limit definition. So the limit as n approaches infinity of the sum from 1 to n of f of x sub k times delta x. Okay, we already found this. That is that right there. 1 plus k over n cubed plus 3. And then we're going to multiply it by delta x, which is 1 over n. Now, again, for the sake of time, because I am awesome at algebra, I have already triple foiled that. So it would be, and this is the limit, and this is the limit. It would be, let me just make sure I'm copying it correctly, 1 plus 3k over n plus 3k squared over n squared plus k cubed over n cubed plus 3 times the 1 over n there. So that, this right here, this portion right here is cubing it. Believe me. Or don't believe me and see if I got it wrong. I can make mistakes. All right, now what am I going to do? I personally like to distribute this in. Some people actually factor it out. I just like to bring it in. So this would be 1 over n plus 3k over n squared plus 3k squared over n cubed plus k cubed over n to the 4th, plus 3 over n. And then, yes, you have to try to rewrite each one as a constant, as a k squared. So I got my little handy dandy sticky note standing by. So let's see. This would be, and again, think about like you're taking the sum of each one of these and you want to leave either a number or the k there. A number, just a number by itself, or just a k or k squared or k cubed by itself. So this 1 over n, I can actually take it out in front, and then I would have a 1 here. Plus this one, I'm going to take out in front the 3n squared, and I would have a k here. For this one, I would take the 3n cubed, and I would have a k squared here. This one, I would take the 1 over n to the 4th, and I would have a k cubed. I'm not writing it all right out here, but I think you get the point. And then this one, again, you can take out the 3 over n, and you're left with a 1 there. Whew, this one's a doozy. All right, now let's see what I got. So the sum of a constant is the constant times n. So this right here is 1 times n, or just n, times the 1 over n. This one would be 3n squared times, what is the sum of k? Using my little sticky note. n squared over 2 plus n over 2. This would be 3n cubed times what's k squared? Woo, running out of room. Plus n over 6. Yeah, I'm running out of room. I got to do these two on the next level. So plus 1 over n to the 4th times k, the sum of k cubed, oof, n to the 4th over 4 plus n to the 3rd over 2 plus n squared over 4. And I'll do this last one. Ooh, thank goodness this one's a good one. Plus 3 over n times the sum of 1. And again, that would be 1 times n. Okay. At this point, I usually get nervous that I made a mistake, but we got this. All right. Let's clean this up. Remember, it starts here and then goes into here. All right. So 1 over n times n is just 1. This one, 3 over n squared times n squared over 2 would just be 3 over 2. 3 over n squared times n over 2 would just be 3 over 2n. 3 over n cubed times n cubed over 3 is just 1. 3 over n cubed times n squared over 2 would be 3 over 2n. And then 3n cubed times n over 6 would be, let's see, 1 over 2n squared. Oof. Now we'll do this one. 1 over n to the 4th times n to the 4th over 4 is just 1/4. This one would be 1 over n to the 4th times n cubed over 2n. Let's see, that would just be a 1 over 2n. This one times that would be a 1 over 4n squared. And this one is 3. Oh my golly. Squeezing it in. Okay, I think I did it right. Now remember, take the limit as n goes to infinity. You would have a 1 plus the 3 halves. This would go to 0 plus a 1. This would go to 0. This would go to 0 plus a 1/4. This would go to 0. This would go to 0 plus 3. Let me handy dandy check that on my calculator. 1 plus 1.5 plus 1 plus 0.25 plus 3. 6.75. I'm going to rewrite this as a definite integral and just check it in my calculator. So this would be the definite integral from 1 to 2 of x cubed plus 3 dx. And, can't see it. Let's see. Math. Down to number 9. 1 to 2 of x cubed plus 3 dx. Boom. Oh yeah. That's a hard one. Hopefully you followed along. All right. See you soon, y'all. Do the homework. You have to do 11 through 16. I've done 2 of them. That means you only have to do 4. Bye-bye.